In this series of videos, we're going to introduce two categories of compounds, each of which has specific behavior whenever the compound is added to water. The purpose of this video is to introduce a category of compounds that we call acids, of which the two examples we're going to start looking at are HCl and H2CO3 that we see here. If we look at their chemical structures and the fact that the compounds share electrons between atoms rather than transferring them, we can see that these acids are examples of covalent compounds, as most acids are. If we take a look at each of their chemical formulas, we can see another common feature in that acids contain a hydrogen, and the hydrogen is almost always going to be the first element found at the beginning of their chemical formula. However, that's where most of the similarities end. HCl is an example of what we call a binary acid, meaning that it is an acid that is made of only hydrogen and one other element. So that's where the prefix bi, meaning two, comes from. We can see from HCl that the second element is also a non-metal, and most of the time in the four most commonly occurring binary acids, the second non-metal is going to be a halogen, as is the case with HCl here. However, if the halogen was fluorine, HF, this would be a different binary acid, as would HBr or HI. So all of these are binary acids in that they contain hydrogen and one other nonmetal, and all of the nonmetals in this case are the four examples of halogens. Now, H2CO3 is obviously not a binary acid because it has three elements rather than just two, so we give it the name oxyacid. Not surprisingly, we call it an oxyacid because oxygen is by far the most commonly occurring element in the chemical structure. However, that doesn't exactly explain how oxyacids form. If we take the hydrogens off of H2CO3, we can see that what we are left with is CO3 with a -2 charge. -2 compensated by the two hydrogens. You will recognize this as a polyatomic ion, specifically the polyatomic ion carbonate. And we can see that oxyacids can form by simply taking a polyatomic ion and adding a specific number of hydrogens equal to the amount of negative charge that the ion has. For example, if we take the polyatomic ion nitrate that has a -1 charge and add one hydrogen to it, we would get another example of an oxyacid. If we were to take the polyatomic ion phosphate with a -3 charge and add 3 hydrogens to compensate for that, that would be yet another example of an oxyacid. And if we choose a third polyatomic ion, let's pick chlorate here, ClO3 with a -1 charge, we can add a hydrogen to that, and that would be yet another example of a polyatomic ion forming a bond with hydrogen in order to form an oxyacid. Now, a third category of acid that will be more commonly looked at in biology as well as in senior chemistry grades is a category that we call organic acids, of which this is one example. Now, if you remember our talk on combustion reactions, you will recognize the term organic in chemistry, referring to compounds where carbon is the central most important element, and many of them also contain hydrogens, such as this acid here. Now, this acid is actually a very commonly used acid in human cuisine. This is actually the chemical formula for an acid called acetic acid that is what makes vinegar taste the way that it does. Now, we can identify an organic acid by looking at a single group of atoms, both in its structure and its chemical formula, and that group is COOH. So organic acids are identified a little bit differently because instead of having the hydrogen at the beginning of the chemical formula, we actually see, if we look at vinegar's chemical formula, CH3COOH, that the hydrogen that makes it an acid is actually found at the end of the chemical formula rather than at the beginning in binary acids and in oxyacids. Now, as mentioned previously at the beginning of the video, acids behave a very specific way when they are added to water, and that being acids undergo what we call the process of ionization. Now, from this word, we can pretty much figure out what it means. We can see the word ion here, and whenever we see a noun that ends in ation, this probably means process or something like that. So ionization is the process of making an ion, meaning that whenever an acid is dropped into water, the acid separates into two different ions, and we can do this with both our binary acid and our oxyacids. So here we know that chlorine as a halogen has 7 valence electrons, meaning it's going to gain 1 electron when it ionizes, and so we would write it as Cl-. And of course we are noting the aqueous state of matter because we are adding the acid to water. Now what's left over is the hydrogen. Now if chlorine is going to gain an electron, hydrogen therefore must lose an electron, and therefore when it loses its 1 electron, it's going to have a positive charge. And this right here, the formation of hydrogen with a positive charge, is how we identify that HCl is functioning as an acid. Now we can do exactly the same thing with H2CO3. We know that our polyatomic ion is carbonate, so we can write carbonate like this for our negatively charged ion. But since this acid here has 2 hydrogens, we would write 2 H pluses that are released when this acid is added into water. And from this, we can come up with 2 different terms based on the number of hydrogens that are released by the acid. So because hydrochloric acid, HCl, releases 1 hydrogen in water, we call it a monoprotic acid. Mono, of course, meaning 1, whereas because H2CO3 releases 2 hydrogens in water, we can call it a diprotic acid, di of course meaning 2. Now from this, if we take this acid here, which has 3 hydrogens, we can extrapolate that this would be a triprotic acid, meaning that it has the ability to lose 3 hydrogens when it is added to water. Now, most people, when they think of acids, automatically think of dangerous substances, such as the destructive acids that are found in car batteries, for example, that can burn through human skin. The vast majority of acids that humans work with, however, are actually quite safe to consume, and for those of you that like orange juice or lemon juice, are actually quite tasty. Now, any connoisseur of orange juice or lemon juice or any citrus-based fruits will recognize that they all have a distinctly sour taste. Now, this also applies to vinegar as well, because our body recognizes acid as being sour. You also probably won't want to get acid on your fingertips, because most people recognize that acid feels sticky and will require you to wash your hands heavily with water in order to get the feeling of acid out of your flesh. And as previously mentioned, vinegar is a common example of acid that is consumed in human cooking, and for any people that like consuming orange, lemon, or grapefruit juice, citrus fruits are all examples of very acidic beverages. So these would be examples of perhaps orange juice or lemon juice as we see in the pictures. This concludes our introduction to acids. In part 2 of this series, we're going to look at the opposing compounds that we call bases and how they react differently when they are added to water.